Okay, we are going to study about hysteresis loop or BH loop or magnetization characteristics of a ferromagnetic core. Let us take a core. Consider we are going to study about BH loop. Before going to the transformer portion, we have to study some basics about basic terms. BH loop and also hysteresis loss, eddy current loss, and some sinusoidal excitation in a magnetic or a magnetic core. Okay, so first we are going to study about BH loop. Consider, just took a core, magnetic core. Here I am drawing a magnetic core in a plane, as a plane, but you have to imagine that it is a three-dimensional core, and we bound a coil on this. Okay, just imagine it is always we draw a magnetic core like a plane in a two-dimensional view, but you have to imagine that it is a three-dimensional view. Okay, so we are mounting a coil on this ferromagnetic core and having n turns of that coil, and we have to give a current I to this, and definitely it will produce a magnetic field, and the magnetic field associated with this magnetic circuit have to be considered. So just consider the length of this magnetic circuit is L. Okay, then the magnetic field intensity of uh, this magnetic circuit H is equal to, we can write it as N into I by L. Okay, so we are considering a magnetic core, and that magnetic core is bound by a coil, and we are giving a current to that coil. Definitely we know that when we given a current to a coil, it will produce a magnetic field. That magnetic field will be associated with this ferromagnetic core, and we consider the length of magnetic core as L, and Ni by L gives the magnetic field intensity H. So now we are going to draw the magnetization characteristics either either H or current in x-axis, I or magnetic field intensity H on the x-axis, and phi or B in the y-axis, either B or phi, flux density B or flux in the y-axis. This is the magnetization characteristics curve. Okay, so we can say this is a magnetization curve or BH loop. We are taking magnetizing field intensity or current in the x-axis, or flux density or flux in the y-axis. This will give the magnetization characteristics of a ferromagnetic material. Okay. So when a magnetic material, just consider this core, when a magnetic material is taken through a cycle of magnetization, the intensity of magnetization and magnetic induction lag behind the magnetic field. Just consider we are giving a current and to the coil, and it will magnetize the ferromagnetic core. So when we increase the current, the magnetization, magnetic field intensity also increases, and it up to saturation. When it becomes saturated, then when we decrease the magnetizing field to zero by decreasing current to zero, what happens? That I and B does not reach zero. This will follow a path like this. So when we pass the ferromagnetic material through a cycle of magnetization, it will pass through this type of characteristics. That means, just assume when we are giving a current, alternating current to a coil, the magnetization and the field intensity will increases, and the magnetic flux density will reach maximum saturation point at here, and then when we when we made, even if the magnetizing field is made 0, the values of I and B are not going to be 0 because it follows a path. Magnetic flux density will not become 0. It follows a path like this. And if we want to uh, if you want to magnetize again in the opposite direction, it will follow another saturation point, and when we try to make the current 0, this will follow another path like this. V and I will not become 0. Okay. So there is a tendency in the material to retain its magnetic properties. So this curve is known as BH, hysteresis curve. So the lagging of I and B behind H is called hysteresis. So the lagging of I and B behind H is called hysteresis. Okay, hysteresis. So when we magnetize a ferromagnetic material by giving a current through the coil, just assume this is a magnetic core and we are giving a current I to the coil. What happens when a current flows through the coil? It will produce a magnetic field. When we increase the alternating current to a maximum value, we know that we always given the current as a sinusoidal form. So through a cycle of magnetization, when the current increases to maximum, the flux density become maximum, B become maximum and saturated. When the current goes through the again to the zero, but does not become zero. The flux density will flux density will produce. Okay. In the first half cycle of the current, you can see here, when it reaches the peak value, the flux density becomes maximum or saturated point. Then, when we decrease the current, the sinusoidal alternating current will reduce to 0. At that time, that magnetic field intensity try to 0, but it will not become 0. The magnetic property will retain at the ferromagnetic core, because even if the current becomes 0, the magnetic flux density will not become 0. Okay, so when the current again passes through the negative half cycle, it goes through another path like this and it becomes saturated in, and it when we try to make again the current to 0, what happens? It attains another Vmax. So minus Vmax to plus Vmax. Okay. So when we try again the current to maximum value, this follows another path like this. That means when an alternating current through the one cycle of that current will produce a hysteresis loop like this. That means the material will retain its magnetic property. That magnetizing field intensity or magnetic flux density does not become 0 again. There will be some magnetic property it will retain in that material. നമ്മൾ ഒരു തവണ ഒരു സൈക്കിൾ ഓഫ് മാഗ്നറ്റൈസേഷൻ ചെയ്യണം. ഒരു ഫെറോമാഗ്നറ്റിക് മെറ്റീരിയലിന് മാഗ്നറ്റൈസ് ചെയ്യുമ്പോൾ വാട്ട് ഹാപ്പൻ, നമ്മളത് ഒരിക്കൽ മാഗ്നറ്റൈസ് ചെയ്യുമ്പോൾ അത് ആദ്യം സാച്ചുറേറ്റഡ് പൊസിഷനിലെത്തും. ദെൻ കറണ്ട് നമ്മൾ മാഗ്നറ്റൈസ് ചെയ്യാന്ന് പറയുന്നത് നമ്മളൊരു കോയിലോട്ട് കറണ്ട് കൊടുത്തിട്ടാണ് മാഗ്നറ്റൈസ് ചെയ്യുന്നത്. സോ നമ്മൾ കൊടുത്ത ആ കറണ്ടാണ് കോസ് ഓഫ് ദാറ്റ് മാഗ്നറ്റൈസേഷൻ എന്ന് പറയുന്നത്. ആ കറണ്ട് നമ്മൾ റിമൂവ് ചെയ്തു, ഇറ്റ് ബിക്കം സീറോ ആക്കി. സീറോ ആക്കിയാലും എന്താ സംഭവിക്കുന്നത്? ദാറ്റ് magnetic property zero ആവുന്നില്ല. For the ferromagnetic material in which that property will retain there. And when we when we force to make it zero by following through a negative half cycle, but it will not become zero, it follows another path. So it becomes a loop for a complete cycle. When we pass the current through a complete cycle, it will produce a loop like this. Okay, so we call, normally it is hysteresis loop. Okay, hysteresis loop. So this is the magnetization characteristics of a ferromagnetic core. Now, what is hysteresis loss? Okay. Hysteresis loss means these iron losses in a magnetic material. This loss is directly proportional to magnetic flux density and also it is directly proportional to number of reversal of magnetism per second, and this hysteresis loss okay, we studied that the magnetization characteristics and that is at in a BH loop. We know that when we try to magnetize a material, it will not pass through the same path. When we magnetize, it will retain the magnetic property in it. So we have to force that means we have to force that material property to become in the initial position, but it will not come back to the initial property, because that ferromagnetic material become magnetized and it will retain that property. So due to this cycle of process, we are using, or we are worked on to come back to the initial property, but it will not come back to the initial property. So this will have some losses in this work. That loss is called hysteresis loss, and this area of this loop will give that hysteresis loss. നമ്മളൊരു മാഗ്നറ്റിക് മെറ്റീരിയലിനെ മാഗ്നറ്റൈസ് ചെയ്തു, ദെൻ അതിനെ വീണ്ടും തിരിച്ച് ഒരു സൈക്കിൾ ഓഫ് കറണ്ടിനകത്ത് നമ്മൾ അതിനെ വീണ്ടും തിരിച്ച് അതേ ഇനീഷ്യൽ പ്രോപ്പർട്ടിയിലോട്ട് കൊണ്ടുവരാൻ ശ്രമിക്കും. ബട്ട് ഇറ്റ് വിൽ നോട്ട് കം ബാക്ക് ടു ദ ഇനീഷ്യൽ പ്രോപ്പർട്ടി. ഇറ്റ് വിൽ ഗോസ് ത്രൂ അനദർ part of loop. That means the magnetic flux density will retain due to that internal property of that material. ഒരു ferromagnetic മെറ്റീരിയലിന്റെ ഇന്റേണൽ പ്രോപ്പർട്ടി കാരണം അതിന്റെ മാഗ്നറ്റൈസേഷൻ അത് റിമൂവ് ചെയ്യുന്നില്ല, അതിനകത്ത് തന്നെ റീറ്റെയിൻ ചെയ്യും. അത് കാരണം നമുക്കൊരു ലോസ് ഉണ്ടാവും. അതായത് നമ്മൾ കൊടുത്ത ഒരു വർക്ക് ഡൺ ഓൺ ദാറ്റ് വിൽ പ്രൊഡ്യൂസ് സം ലോസ് on that ferromagnetic material. That loss is known as hysteresis loss, and the value, some calculations given that reveal that hysteresis loss is the area of this loop. For each material, this area will be different. That hysteresis loop area will, for steel, the area will be less. For another material, conducting material, area will be high, like that. So that area of that loop will give how much the hysteresis loss. Okay. So hysteresis loss is an iron loss. The loss is directly proportional to the maximum flux density. That means this Vmax and minus Vmax. It depends on maximum flux density and also volume of iron core. Volume of iron core. That means that volume of iron core or area of loop. It depends on area of this loop. Okay. Another one we are going to study is eddy current loss. Eddy current loss. Eddy current loss means ഒരു മാഗ്നറ്റിക് മെറ്റീരിയലിന്റെ പ്രോപ്പർട്ടീസ് ആണ് നമ്മൾ പറയുന്നത്. ഫസ്റ്റ് നമ്മൾ പറഞ്ഞു ഒരു മാഗ്നറ്റൈസേഷൻ ക്യാരക്ടറിസ്റ്റിക് കർവ് പറഞ്ഞു. ഇനി ഈ മാഗ്നറ്റിക് പ്രോപ്പർട്ടി റീറ്റെയിൻ ചെയ്യുന്നത് കാരണം ഉണ്ടാകുന്ന ലോസ് ആണ് ഹിസ്റ്റെറിസിസ് ലോസ് എന്ന് പറഞ്ഞു. Now we are going to study another loss in a ferromagnetic material. So just consider a magnetic core. I'm just here considering a magnetic core. This is a three-dimensional magnetic core, and we have wound a coil is wound on this magnetic core, and we are giving current. Current I is flowing through it. So the current direction will be like this on this coil. Okay. So we know that when current flowing through the coil, definitely it will produce a magnetic flux. So just assume this will be the magnetic flux direction phi. Okay. So this is the magnetic flux. Okay. I'm just marking the magnetic flux in another. Okay. So always current direction and the magnetic flux direction will be 90-degree phase difference with each other. So we are marking this direction of flux like this on the magnetic core. Okay. Now, when we given a current, that means usually it is a sinusoidal current or alternating variable current will be applied to that coil. When we apply an alternating current, there will be rate of change of flux. The flux produced will be a varying flux. When we are giving an alternating current, it will produce an alternating magnetic field. So there will be some rate of change of flux in it. That rate of change of flux will produce an induced EMF E in it, in the core. An induced EMF in the core will be produced. Okay, we are considering the core. When we wound a coil on a magnetic ferromagnetic core, the current flowing through it will alternating current flowing through it will produce an alternating magnetic field. So the flux phi, there will be a varying flux. That means there is a rate of change of flux in it, and it will produce an induced EMF in the core. If there is another coil here, if another coil which is placed near to this core, due to this induced EMF or magnetic field linked with it, a mutual induction induced EMF will be produced in another coil also. Okay. Anyway, this induced EMF is due to the alternating if the core. Okay. And that we know that the magnetic core, just consider the magnetic core. This magnetic core is a conducting material, so definitely there will be a current flow inside that magnetic core, thick material. So this magnetic core, inside this magnetic core, there will be a current generated, I will be generated due to this rate of change of flux. There is an induced EMF, and in turn this induced EMF will generate a current in the ferromagnetic core. This current is known as eddy current. Okay, that means when we given a current through this coil, that ferromagnetic that coil will produce a varying magnetic field in it, and that flux will be a rate of change of flux, and that rate of change of flux will produce an induced EMF in the ferromagnetic core. We know that all the ferromagnetic cores are metals, so in which there is a current will be generated. That generated current in a ferromagnetic core is known as eddy current. So we know that if there is low resistance on that ferromagnetic material, conducting material, the resistance is low ആയിരിക്കും. So if the resistance is low, then it will produce large current, and that current will flow in all directions in that thick material. So that current is known as eddy current, and that eddy current will in turn produce a large I square R loss in it, because it's an unwanted current in that magnetic core. Actually it's a transformer action. We can see we are, normally in a magnetic core we wound a coil, and it will induce another EMF in the secondary coil, and load will be placed on the secondary coil. This is a transformer action, but actually another current generated in the core itself, magnetic core, it is an unwanted current, so, and it will produce large I square R loss in the magnetic core. So it's an unwanted loss, and that loss is known as eddy current loss. This eddy current loss. Okay. Then this is an unwanted loss, and we have to overcome these losses. How to reduce this eddy? We cannot eliminate that loss completely. We can reduce that eddy current loss by reducing that current flow. That means we know that it's a ferromagnetic material. When we actually we are taking a thick core, we are taking a thick core as our ferromagnetic core on a transformer. Okay, now we know that if the current flow on the coil is on this direction, and the magnetic flux lines will be in this direction. So the current generated on the core will be either into that core or out of this core in this direction, perpendicular. That means flux and our current and voltage both are in the mutually perpendicular direction. So if the flux lines are in this direction, you know that flux lines will be taken in this direction, and current will be like this into that core or outside that core. We can mark it as dot or cross like this. അതായത് ഫ്ലക്സും പ്രൊഡ്യൂസ് ചെയ്യുന്ന കറണ്ടും പെർപെൻഡിക്കുലർ ഡയറക്ഷനിലായിരിക്കും. അപ്പോൾ ഈ ഒരു ഡയറക്ഷനിലായിരിക്കും മാക്സിമം കറണ്ട് ഫ്ലോ ഉണ്ടായിരിക്കുക. സോ ഹൗ ടു റെഡ്യൂസ് ദാറ്റ് എഡി കറണ്ട്? ജസ്റ്റ് കൺസിഡർ വെൻ വി take a magnetic sheet of metal, then again another sheet of metal is stick on that and first metal sheet, and we are placing a varnish or paper, an insulating material in between that, and again we are taking another metal sheet and stuck on that another sheet, and similarly we are placing more and more sheet and make the same thickness of core. Okay, in order to make a single core, we are taking the number of sheet of metals, ferromagnetic material, and we are stick each one on the another metallic sheet by varnishing, by putting a varnish or paper in between each ഷീറ്റ്. ഓരോ ഷീറ്റിനിടയ്ക്കും നമ്മളൊരു തിക്ക് കോർ എടുക്കുന്നതിന് പകരം എന്ത് ചെയ്യുക, ആ തിക്ക് കോറിന് നമ്മൾ ഡിഫറെൻറ്റ് നമ്പർ ഓഫ് ഷീറ്റ്സ് ആയിട്ട് സെപ്പറേറ്റ് ചെയ്യുക. ദെൻ വി ആർ സ്റ്റിക്കിംഗ് ഈച്ച് ഓഫ് ദ ഷീറ്റ് into that and make whole core in the same thickness. And before that we are placing varnish or paper, that's some insulating material in between each of the sheet. മെറ്റാലിക് ഷീറ്റിൻ്റെ ഇടയ്ക്ക് ഒരു വാർണിഷോ പേപ്പറോ കൊടുത്തിട്ട് ഇൻസുലേറ്റ് ചെയ്ത് ഓരോന്നിനെയും തമ്മിൽ ഒട്ടിച്ചൊട്ടിച്ച് ടോട്ടൽ ഒരു മാഗ്നറ്റിക് കോർ ഉണ്ടാക്കും. ഒരു സിംഗിൾ കോർ, ഒരു തിക്നെസ് കൺസ്ട്രക്ഷൻ കോർ എടുക്കാതെ നമ്മൾ നമ്പർ ഓഫ് മെറ്റാലിക് ഷീറ്റിന് തമ്മിൽ ഒട്ടിക്കും. ആ ഒട്ടിക്കുന്നതിനിടയ്ക്ക് ഒരു വാർണിഷോ പേപ്പറോ പ്ലേസ് ചെയ്തിട്ടാണ് നമ്മൾ ഈച്ച് ലാമിനേഷൻസ് വെക്കുന്നത്. വി കോൾ ദിസ് മെറ്റാലിക് ഷീറ്റ്സ് ആസ് ലാമിനേഷൻസ്. ഓക്കെ, laminations എന്നാണ് പറയുക. So each laminations are insulated with each other by varnish or paper. Okay, so the current flow from one sheet to another coil will be restricted. Whole current flow cannot be restricted, but we reduce either 1/5 times or 1/8 times. It's just an example. We can reduce that total eddy current produced in the single core by this much in the laminated core. So we can reduce the eddy current loss by laminating the ferromagnetic core. Okay, so hysteresis loss and eddy current loss are the main losses or iron losses produced in a ferromagnetic material. Okay, hysteresis loss എന്ന് പറഞ്ഞാൽ it will be ഒരു ഫെറോമാഗ്നറ്റിക് മെറ്റീരിയലിനെ നമ്മൾ മാഗ്നറ്റൈസ് ചെയ്ത് ത്രൂ ഔട്ട് എ മാഗ്നറ്റൈസേഷൻ സൈക്കിൾ, it will not come back to the initial property, it will retain the magnetic property. So due to that there will be some losses due to the inherent property of that ferromagnetic material. That loss is known as hysteresis loss. Okay, and by taking proper material we can reduce the hysteresis losses. For each material the thickness of that loop, hysteresis loop may be less, so we can reduce the hysteresis loss. For steel, cast iron, the loop will be higher thick, and for steel it may be less thickness. That means by using steel, cast steel as a magnetic core, we can reduce the hysteresis loss. Cast iron ആകുമ്പോൾ hysteresis loss കൂടുതലായിരിക്കും. We know that hysteresis loss depending on the loop area. So if the loop area of the material is high, then hysteresis loss will be high. If the loop area is less, then the hysteresis loss will be less. So by taking suitable material, we can reduce the hysteresis loss. And how can we reduce the eddy current loss? Eddy current loss means it is the leakage current produced in a ferromagnetic material. നമ്മളൊരു കറണ്ട് കൊടുക്കും, ഒരു കോയിൽ ഒരു കറണ്ട് ഫ്ലോ ചെയ്യണം, ഒരു ഫെറോമാഗ്നറ്റിക് മെറ്റീരിയൽ പ്ലേസ് ചെയ്തിരിക്കുന്ന കോയിലിൽ കറണ്ട് ഫ്ലോ ചെയ്യുമ്പോൾ there will be an alternating flux, and that flux will induce an EMF in the core itself. That EMF will produce a current because the current in the magnetic core, because that magnetic core is a metal, so it will generate a current inside the magnetic core. That leakage current is known as eddy current, and leakage current will always produce a loss. That loss is known as eddy current loss. So this eddy current loss can be eliminated by using laminations. That core is laminated into different metal sheets, and we are placing or insulating that laminations with each other and sticking on each lamination and making a whole core, and we can reduce the eddy current loss, but we cannot eliminate the totally that eddy current loss and hysteresis loss. We can reduce that losses. Okay. So hysteresis loss can be reduced by selecting suitable material. Eddy current loss can be reduced by laminating the magnetic core. Okay. Now there is another thing on magnetic core, sinusoidal excitation. Just I will explain what is sinusoidal excitation of a magnetic core. Okay. Sinusoidal excitation in a magnetic, just assume a core which is wound by a coil, and we are applying an alternating voltage to it. Just assume a core inside this. I am just showing only the coil. Okay, and we are applying a voltage in it. What happens? An alternating voltage is given to a coil. It will produce a flux in it. A phi will be produced in it in a particular direction. We know that if we are giving an alternating voltage, the produced flux will be also alternating one. So there will be a rate of change of flux d phi by dt will exist on it, and it will induce that rate. We know that whenever there is a change in flux, it will induce an EMF. So we can write the V as equal to, in terms of inductance, L into, because there is a coil, L into di by dt, and we also already defined that L is equal to N into d phi by dN, or we can in turn it is represented as, which is proportional to N square by reluctance, or so it is depending on reluctance or permeability of the material, ferromagnetic core. Okay, so from this, that means inductance depends on the material property, reluctance or permeability. Reluctance, permeance will be an inversely proportional property, so inductance depends on the reluctance also. So we know that property, due to this inductive property, current lags behind the voltage. So when we represent a magnetic core in as an electrical circuit, we have to consider this inductance value. Because of this inductance, current lags behind voltage. So we have to represent the magnetic core as a coil. We have to, നമ്മളൊരു മാഗ്നറ്റിക് പ്രോപ്പർട്ടീനെ എപ്പോഴും ഒരു ഇലക്ട്രിക്കൽ സർക്യൂട്ടായിട്ട് റെപ്രസെന്റ് ചെയ്യണം. എപ്പോഴും അതിനൊരു ഇലക്ട്രിക്കൽ പാരാമീറ്ററിലോട്ട് ട്രാൻസ്ഫർ ചെയ്യണം. അപ്പോൾ നമ്മൾ നോർമലി ഒരു മാഗ്നറ്റിക് സർക്യൂട്ടിനെ റെപ്രസെന്റ് ചെയ്യുമ്പോൾ, അതായത് ഒരു ഫെറോമാഗ്നറ്റിക് മെറ്റീരിയൽ ഒരു കോറിനെ എങ്ങനെയാണ് ഇലക്ട്രിക്കലി റെപ്രസെന്റ് ചെയ്യാന്നാണ് പറയുന്നത്. സോ we have to represent that electrically as a inductive coil, because there will be a property of inductance L. Due to that L, current lags behind voltage, so that inductance will depends on the voltage value. There is an effect of voltage, so we have to mark it as a we have to take it as an inductor. And also in the magnetic core we have studied two types of losses, hysteresis loss and eddy current loss. So normally, usually in an electrical circuit, the losses are represented by resistors, and we are taking these both in a parallel connection. So we usually represent the or magnetic material or magnetic circuit as a resistor in parallel with the inductor coil. I will again explain. Okay, so we know that in a ferromagnetic material there are two types of losses, hysteresis and eddy current losses. We are going to represent our magnetic core in an electrical circuit. As an electrical circuit, we are going to represent as an electrical circuit. When it's sinusoidally excited, that there will be some flux in it. Okay, I here already shown that when we given an alternating voltage to a ferromagnetic material or magnetic circuit, there will be a rate of change of flux in it. That rate of change of flux will produce an induced EMF, and so we can write it as V is equal to L into di by dt. That means there is a property of inductance, so we can represent that as an inductor coil due to this property. Okay, so we can represent the magnetic circuit as a coil. Then for a magnetic circuit, there is another property, hysteresis, and also a leakage current, eddy current. Due to these two properties, there will be some losses in that magnetic material. So we have to consider that also. So we represent a coil, magnetic circuit in a resistive manner also. So we can connect that resistor and inductor in parallel. Why we are connecting it in parallel? Because both of these quantities are depending upon the voltage applied on it. Hysteresis and eddy current loss also proportional to that voltage, and also our inductive property, the inductance. Due to this inductance, current lags behind the voltage, so we have to consider that also. So the inductance also depending on the have the effect on voltage on it. So we are represent both hysteresis and losses, and that inductance property of a magnetic circuit will affect same with the voltage. So effect of voltage on both inductance and hysteresis loss and eddy current loss will be same. So we can represent it. Voltage effect is same, we can represent it as a parallel connection. If there is which are depending on current, if current are same, we represent the circuit as series. If the voltage is same, then we represent a circuit as parallel. Okay, ഒരു സർക്യൂട്ടിലെ വോൾട്ടേജിന്റെ എഫക്റ്റ് ആണ് സെയിം ആയിട്ട് വരുന്നതെങ്കിൽ നമ്മൾ ആ സർക്യൂട്ടിലെ എലമെന്റ്സിനെ പാരലൽ ആയിട്ടാണ് റെപ്രസെന്റ് ചെയ്യുക. ആ സർക്യൂട്ടിൽ കറണ്ട് ആണ് സെയിം ആയിട്ട് വരുന്നത് എലമെന്റ്സിലെങ്കിൽ നമ്മൾ അതിനെ സീരീസ് ആയിട്ടാണ് റെപ്രസെന്റ് ചെയ്യുക. ഓക്കെ, ഇങ്ങനെ സീരീസ് കണക്ഷനിലല്ലേ കറണ്ട് ഫ്ലോ സെയിം ആയിട്ടുണ്ടായിരിക്കുക. പക്ഷെ ഇവിടെ ആണെങ്കിലോ കറണ്ട് ഫ്ലോ സ്പ്ലിറ്റ് ചെയ്ത് ഡിഫറെന്റ് കറണ്ട് ആയിരിക്കും രണ്ട് ബ്രാഞ്ചസിൽ വരിക. അപ്പം നമ്മൾ വോൾട്ടേജ് എഫക്റ്റ് സെയിം ആണെന്ന് പറയുകയാണെങ്കിൽ നമ്മൾ ആ സർക്യൂട്ടിനെ പാരലൽ ആയിട്ടാണ് റെപ്രസെന്റ് ചെയ്യുക. So a magnetic circuit can be represented electrically but like this. So this will be our electrical representation of a magnetic circuit. Okay, thank you.